Now that it seems that most of you are in, it's good time to unplug and welcome Kevin for the first talk of the afternoon. So, Kevin Brown, and as you have been instructed, you have to read the bio, but personal friend, I thank you for coming. And I also want to highlight that he's the chair of one of the conferences called the Latin America High Performance Computing, Carla, which he is chairing it in a place nearly as cool as New Zealand. It's Jamaica. So in September, some of us are going to Jamaica, but we are going not to talk about that. Kevin.
All right, so just to contextualize the talk, Nicholas invited me knowing that I'm early career. So I don't manage a center or run big programs. And as I was saying to Nick earlier, early career folks only go to places when they can get certain things from it. Like I need some citations, I need some new collaboration, someone to include me on some projects. So I'm going to talk a little bit about the really technical thing I'm doing. And if it applies to you, then please feel free to cite my work and reach out for collaborations. He also said that we should talk about something about myself that's not included online. So Kevin A. Brown, I always include the A because there are many Kevin Browns. In fact, there are 2 Kevin A. Browns at Argonne. And I put researcher because research is not really my passion. I call it my medium. Typo. Now, where my passion lies is event planning, program development, and community building. And on the right here is a Halloween party I organized last year at Argonne. And in the US, Argonne is one of the Department of Energy's labs, so DOE. So what we called it, we had the Department of Entertainment Fun Opportunity Announcement. And there was an FOA number associated to the party and application date where the party is. And there's an after party as well, so there's follow-on fun, not follow-on funding, and that was a point of contact. So I organize a lot of these things for community building and so on because that's really my passion. Now, another thing about me that I'm positive is not available anywhere online. I am a prize-winning cheerleader. So, thank you. I did undergrad in Jamaica, where I'm from, then grad school in Japan with Satoshi. And while at the University of Technology in Jamaica, my team won the silver medal and the bronze medal for cheerleading in the interdepartmental cheerleading competition. So, yeah, I don't know how to tumble and do all those things, but I know how to throw people and catch people.
It has a DOE 5 on the bottom to be cool.
It's true.
Will there be a reason to throw people this week?
Sure, we can, we're creative folks. Yeah, we'll make it happen. So the topic of my talk is pathways to actionable ModSim for computing infrastructure. And in previous talks, I highlighted actionable ModSim because, the goal of the presentation is to say, we're doing modeling and simulation, but we need to be able to do it in a way where the information is actionable, meaning it comes in a timely manner and it has an accuracy that we can use for design, deployment, management, and so on. In this talk, because I want to try to throw some big questions out there that I can't answer, and hopefully folks in the audience will be able to help with that answering, I talked about the pathways. Kind of at the end, I'll discuss, I would say, some of the challenges early career folks like myself and my peers are facing in the space of ModSim. And since ModSim we think is a really critical part of moving forward in terms of building new technologies, if these challenges aren't addressed, we're really going to continue limiting the field, limiting the growth of researchers and so on. So as an early career person, I come to you with all my ignorance laid bare. Tell me where I'm wrong, tell me where I'm not seeing things, tell me where my generation is going off base, and we need to, recalibrate in order to do things in the way you all did it in the golden years of steady state funding and, monopolies in industry, so you could do everything you want without competition. Huh?
You're being sarcastic.
No, at the end, I'm going to mention a book I was reading about Bell Labs, and Bell Labs thrived when it was a monopoly because they could do long-term things and invest for however long they want. But these days, I have a project that's 2 years, and people want returns every 6 months. So I feel like I'm in the industry sometimes, even though I'm supposed to be in basic research. So we all know this, but just to recap stuff, I know one thing I didn't say at the beginning of my talk is I think I'm this year's poor replacement for Adolphe. Adolphe is our resident ModSim person, and I'm sure he has a lot more knowledge of this domain than I do, so bear with me and correct me whenever I go off base. So our computing environment, can it get any more complex? We're always trying. I think, that's our goal every day. So, there are new scientific grand challenges. We're going from 25 kilometers squared resolution for climate models to 10 to 5. Now we want to go to 1, and Rupak wants to go to 1 meter squared. So that's the new scientific grand challenge that we're going to address, or we're going to try to address. And we're integrating emerging compute, memory, storage, and networking architectures. Larry and this team from HPE, they're throwing out new Slingshot and Rosetta designs like crazy. And we've got to include this in our architectures and include them in the modeling of the whole architecture. And where behavior is concerned, I'm talking about performance, reliability, energy, and efficiency. Of course, this impacts our scientific and technical productivity. Now, when I talk about the computing infrastructure, I'm talking about from one node or a processor on the Aurora supercomputer to the entire rack, to our entire distributed research infrastructure in the DOE, the Department of Energy, where we have an ESNet wide area network connecting most of our scientific facilities and going all the way to CERN in Europe, where we exchange data and help share computing resources. Now, to really understand how everything works, we need to be able to model it at all scales. We need to know what's going on at the processor, at the networking level, and also at the wide distributed level. So it's really difficult, and so it's really hard to predict. But unpredictability is costly. We're talking about the things that really matter to everyone: money, time, and productivity. So where money is concerned, these systems cost hundreds of millions of dollars. And as our first speaker said, you spend a few hundred millions of dollars buying this system with GPUs, and then you find out 50% of your time is spent in the network. You just lost 50% of your investment because you couldn't predict what was going to happen before you build it. Then time. Acceptance testing and shaking out a system. Tuning these things requires entire divisions and teams and facilities and industries coming together, just trying to get all the knobs configured in the right way so they all work together so that we can achieve 50% of what we wanted to achieve. And this takes a lot of time. And then where productivity is concerned, we don't want our scientists spending days and hours trying to solve bugs and fix things that are supposed to work, but they just don't work, and it's really hindering their productivity. So we cannot, at least, let me not say we cannot because we've been doing it for a while, we should not continue to live with the unpredictability. We are wasting a lot of things, and we are leaving a lot of money, time, and productivity on the table. Now, I'm going to give a quick ModSim primer for those who may not have seen Adolphe's talk. So I work in an area called parallel discrete event simulations, and how that works is we look at an entire system and we think of what are the salient events that will happen. What do these events do, like a packet arriving on a router? And then how long will these events take? And which other events do these events create? And we simulate the flow of events through the entire system. So they're commonly used for modeling compute architecture. They're also used for hospitals, queuing, manufacturing, and production lines. These event-driven models, they encapsulate the salient activities in the architecture. And they're predicting emerging behaviors of what happens. If we can predict what happens at the packet level, then when all the packets in the system, we'll see how congestion forms, spread, and so on. So we need to be able to do it at a very fine grain in order to see what happens at a very large scale. as accurately as possible so that RUPAC will accept our code. And designing these models depend on the type of study being done, meaning the type of fidelity we need, and the type of outputs we want from it. Are we predicting facility scale? Are we predicting architecture or component scale? And so these are some of the events that will happen in the system, and we need to simulate these things, and we're trying to parallelize them by splitting these events across multiple nodes, but they're time dependencies. So then we need time warp systems or conservatives or optimistic predictions. We need to be able to do rollbacks if we predict something optimistically and it's wrong. So the point I'm making here in this ranting, which is causing confusion, is that it's complex and it actually is very confusing. One of the biggest issues we have with writing parallel discrete event simulation code is that if you're predicting optimistically and your prediction fails, you need to roll back the system. But the system is already so complex and there's so many dependencies that writing rollback handlers effectively is a big problem. People have been trying to use AI to automatically generate rollback handlers, but that's not really working out really well. Anyways, why is predictability so hard? I'm going to give a lot of text. Bear with me for a second. So infrastructure design and operational complexity. These systems are big and complex, and everybody wants to do everything on the system all at the same time. So to understand it before we can model it, we need to understand the system design, the metrics, the data being collected, the data analysis process. There's a computational complexity to these models, like simulating 200 milliseconds of activity on a 8,000 node network can take 6 hours. Now, I actually want to simulate the entire campaign of predicting the climate for North America, but that's going to take weeks. Not practical with this type of simulation that we have. So the high fidelity models, they capture salient properties, but they're not scalable. So how can we accelerate them, and how can we limit the simulation fidelity without losing accuracy? Big questions. Heterogeneous components benefit from different modeling approaches. Some may use PDES, some may use machine learning models. How can we decompose the infrastructure in a way to know which modeling approach to use, and then compose a model using multiple methodologies? Very difficult. And then interconnected components need ways of interconnecting these models, as I mentioned. So, for example, combining a PDES simulation with an agent-based model is very difficult. Now, how can we do better? And this is where I'm going to highlight some of the work I'm doing, so cite it if it sounds interesting. So we need to build better models, and in order to do that, we need to understand the system. So we need to benchmark, monitor, and do performance analysis in rigorous and robust ways. We need knowledge extraction from the design documents so that we can make sure that our models are accurate to the systems that they're modeling. I need to be able to validate these models against real systems. And I'll talk about how difficult this is in the next couple of slides. These simulations that are taking hundreds of years to run, if we actually try to run them, we need to find ways of accelerating them. We tried optimistic, we're trying multi-resolution by using machine learning and PDES. And we want to leverage GPUs and other accelerators, but we are nowhere close to be able to doing these things with our discrete event simulations because we don't have funding to do it. And dealing with heterogeneity and interconnectedness. So multi-resolution, multimodal models, like if you have an entire system, how do you vary the resolution based on which component you're modeling? That's one. And then looking at the bottom, unified ModSim infrastructure, at the top, we're looking at different approaches that we're going to connect to compose the entire system. At the bottom, we're talking about what if you could build a single simulation infrastructure that you can use to run PDES, agent-based modeling, and everything. So if you have an entire ecosystem, like a hospital or the healthcare sector in your city, you can model the hospitals and their queuing delays and the processes using PDES. Then you can model the spread of a disease throughout the city using an epi-modeling, agent-based models. Then you can model the transport system that will be affected during COVID by using the PDES or something else, or system dynamics in other ways. And having this underlying infrastructure that everything can use will enable us to really effectively model everything and their interrelatedness in order to get actionable information about it, knowing that everything is really captured in the system. Now, talking about accelerating simulation, and we're combining PDES and surrogate, I'll jump through these slides. So this is how a PDA simulation will look once we try to decompose it. At the top, we have workload, your application, climate science or fluid dynamics. Every message you send in your application will create a number of events for messaging events. And each of those events will create hundreds of packetization events, which then create more link transfer events. And this really creates an explosion of events. So you could be talking about hundreds of billions of events that you need to simulate for just one system. Now, with machine learning, however, if you have a well-trained model with rich data sets, you could predict exactly how long that application will take in just one step. So the order of speed up is tremendous. But the issue here is you need a lot of data to be trained on. And if you don't have sufficient data about how things work in an environment like a system you never built before, how do you get data to train that model in order to predict what's going to happen in a novel architecture? So what we've done is we've created a simulation approach which runs the high fidelity simulation for a few time steps, generate enough training data to train our surrogate model, switch the simulation completely to surrogate model and predict far into the future. Then when something changes in our environment, like a new application enters the system or something finishes or there's a failure, the surrogate model is no longer accurate. So we can switch back to high fidelity, run again in high fidelity, generate new training to retrain different surrogate models. So we have phase-specific surrogate models that we can then use, and we don't need as much training data to predict what's going to happen in a novel environment. And the crux of all of this lies in something we created for Director. And this Director allows us to connect two independent running models. You could have your surrogate model running on a Cerebras cluster or a SambaNova cluster while your PDAS is running on your main supercomputing cluster. And they're talking to each other over ZMQ. And the Director will orchestrate the switching, and everything is done dynamically. So you never really need to bother with your simulation or even worry about what the simulation is doing and whether or not this is surrogate applicable or not. The simulation will decide. And our demonstration, like in using 50%, in using the surrogate for 50% of the simulation, we're able to speed up by 2x. So there's almost like perfect speed up by using a surrogacy. The overhead from doing this communication to a ZMQ server is less than 1%. And the Director that does this orchestration incurs less than 2%. So we think this is a very viable approach, turning very complex long-running simulation in a scalable way to give us some quick actionable information. And we're seeing our loosely coupled hybrid simulation help us to deal with simulation complexity while also ensuring that the model are accurate for heterogeneity or heterogeneous components. Now, for the bigger picture, what's next and what's missing? As I mentioned, we need more comprehensive benchmarking and evaluation of large-scale production infrastructure. When we get a new system at Oregon, and this is, I'm sure everybody experiences it in their center, the vendors work really hard to get us to acceptance testing and check all those milestones in the contract, and then they hand it off to us. And the facility is really eager to get the system into the hands of users to be productive. But very little time is spent actually benchmarking the system in production, taking it offline for a week or a month to really understand how it works. Because we're building large-scale networks, and we, at least from what I've seen across the US, we hardly spend time studying large-scale networks because the facilities that have these large-scale networks just really want to be doing the work of, running the science. Let me not worry about the testing. We need better models of middleware and software services, like DK Panda's ENVA pitch. To the best of my knowledge, we try to make accurate models of HPC systems and HPC applications, but we're always missing what the MPI layer is doing, what the IO subsystem is doing. And we know that's a lot of headache in terms of tuning. So we need to develop better models in these areas. We need, I think, new ModSim paradigms that incorporate new algorithms, programming models, and architectures. A lot of the paradigms and technologies and algorithms we're using in ModSim is 20, 30 years old, probably even 40 years old, from the from Georgia Tech in the 1980s when they were developing time warp and PDAs. So I don't feel like we've actually progressed a lot in recent years because there's this disconnect between people who are doing fundamental ModSim research and people who are applying ModSim. The fundamental ModSim research don't really have any money to do much and progress it. The people who are applying it, like myself in HPC, our time is spent, just trying to build models of our system, which is really hard and time consuming. And I don't have the expertise to build new modeling paradigms. Well, now we have some funding to delve into that. So yeah, these are some, I think, are things that are missing in our environment that I don't feel like anyone has proposed creative solutions to, although it's going to require a lot of money in different cases. And if folks here in the audience have ideas or know things I'm missing, totally happy to hear it. Now, a reason I wanted to talk about some of the challenges we're having, and I read this book, The Idea Factory, Bell Labs and the Great Age of American Innovation by John Gertner. And for those, I wasn't aware of this until I read the book. For those who were like me, pre-book, Bell Labs is where the transistor was developed, GPS, radar, I think, and a lot of other things that we can think of. And that's because, they had a system, an ecosystem that could really just have innovation thrive and support it to maturity. Now, John Pierce, the one who coined the term transistor, he mentioned some principles that he felt were effective to make Bell Labs as productive as it was. And so I'm saying these are pathways for supporting long-term impact for research. One, he said, a technically competent management all the way to the top. I'm sure we'll all agree with that. I'm not going to talk much about it because I want to be a bit controversial, but not too controversial, because my management may see this talk. Researchers didn't have to raise funds. Enough said. Next, research of a topic or system could be and was supported for years. So these days when you have, in industry or so on, maybe 3 months to show some returns, or 6 months, or in the DOE and other spaces, 2 to 5 years to show some returns is very difficult. And research could be terminated without damning the researchers. So it was okay to try risky things and fail, and not your career fail and nobody will ever work with you again. So I think because of a lack of that fourth item right there, and I mean, other things I'll talk a bit more about, but that fourth one, people don't do risky things. I've seen a lot in basic research as what I would read about in these books. I mean, maybe it's happening, I don't see it, as I say, point me in the right direction, show me the light. But it's really hard. And so when I'm writing proposals now, there's something really exciting I want to do. But then when I submit that proposal, even a paper, not even a proposal, I submit the paper or the proposal, and you're just thinking that reviewer who's going to say, yeah, this is not going to work. So then you scale back, your risk, the risk-taking behavior, and you give something which seems very plausible and more realistic. But then we're always making incremental progress. Contrary to in the past, and people could have these big ideas, big dreams, come to multi-core world and say, we're gonna solve world hunger using supercomputers, and here's how we're gonna do it. And you don't go back to your institution saying this anymore because they're like, yeah, focus on this thing, get the system working, basically. So this is my last slide, and I'm titled Challenges that we're not solving. So as I mentioned, it's hard to build and validate models due to limited understanding of the environment. We're doing insufficient large-scale benchmarking for supporting better ModSim. So if you have a facility and it is, you have the power to say, we have this system running for a few years now, we're planning to build a new system. People do some benchmarking here and there. How about we take it off? No, I'm not saying take it offline. I'm being grandiose here now. How about we take it offline for a month and give it to an entire team of researchers or entire collaboration of researchers and say, do as much as you can. You have full access to the system, all the logs that come from it, and let us know everything about this infrastructure before we actually spend another $100 million building a new one. And then once we've built it, we realize, the network is not actually behaving, or the GPU, CPU integration is not working as we want. So can we do something like this? This type of rigorous benchmarking that is more meaningful. ModSim lags algorithmically and technologically. And as I mentioned, there's limited funding or incentives for fundamental ModSim research. It's not very sexy. Building a new chip is awesome. Building a new simulator to simulate this new chip accurately, let's tack it on to some other project that exists, right? And then there's folks don't share in order to stay competitive because everybody's going after the same piece of pie. And different places work differently, I've seen, but like in university or places that are more basic funded that operate on soft money, if you start talking about your ideas and the interest you have, the big dreams, before you get them funded or write them in a proposal, someone else might scoop you and get that thing funded before you do. And that leads me into saying that basic scientific research silos, from what I've seen, they're persisting, at least for the early career level. Most folks are employed to work on their supervisor's project and do these things to further your supervisor's goals. And oftentimes supervisors are benevolent and will say, this will help you to grow, but at the end of the day, you're still working within a box that your supervisor defines. And so like ModSim researchers and HPC researchers are often in two different worlds. Last year, I started going to ModSim conferences where there are folks from Disney talking about how they're simulating their new rides and people going throughout their parks. And I'm like, the changes they're making in order to make their simulations effective, we should be doing them for HPC, but we're not often doing them. And there's limited incentives to reach these silos oftentimes because as the early career folk, as I mentioned, like, I'm going to apply for my green card later this year, and one of the checkboxes I need to make is that I have certain number of citations and I have certain number of publications. So for the next year or so, every event I go to, I'm thinking, all right, how does this get me to check that box? And oftentimes, it's easier to guarantee return on investment in known environments. So I'm not going to go too far off base here. And inadequate training for next generation researchers. Now, this is, I don't know if it's more controversial, everyone's going to agree. So I think the training is oftentimes optimized for short-term returns. Do this type of work, you'll get it published quickly before somebody else scoops you, as opposed to let's try to solve this big problem that we're not sure can be solved yet, but it's going to be really impactful for everyone. And the incremental work is often preferred and even incentivized, as I've alluded to. And oftentimes, researchers don't speak engineering or industry, or vice versa. And so it's hard to coordinate and collaborate. And one of the things that came out of the Bell Labs, I'm going to finish here, is that because they had one mission of building out this technology and so on, they had incentives in place to ensure whatever they were doing, they could talk to people and explain to them how to scale it up and so on. So yeah, these I think are challenges we're not solving, and I hope this community can take a hard look at them.
Thank you very much.
Oh.